Hello and welcome to another TensorFlow tutorial. Today I'll be showing you guys how to implement transfer learning using models that you can find on TensorFlow Hub. We will be going through two types of transfer learning. They are feature extraction and fine-tuning. Before we get into what the differences are, I want to let you guys know that we'll be using the ResNet 50 architecture, and you can actually see the architecture over here in this picture. Feature extraction is when you don't train the weights that are in this red box over here. So what happens in this scenario is that the ResNet architecture actually spits out a feature vector. It'll be like this feature vector will come out of this fully connected 1000, and then we'll feed it this dense layer. So yeah, it spits it out. In this case, it would be 1000 features per image. This is then given to our dense layer over here, that has the weights that we will actually train and will learn the patterns of this feature vector. The dense layer will then output the probabilities of which class it thinks the model is, well, the picture is. So fine tuning is similar to feature extraction except for one important fact. The fact is that you actually train the weights inside the ResNet architecture as well as the output dense layer. Swapping between the two is pretty simple in TensorFlow. You just have to change a false to a true or a true to a false. So the dataset that we'll be using is the Intel image classification dataset. It can be found on Kaggle with this link over here. I'll post it in the description. And it's basically just classifying between images of buildings, forests, glaciers, mountains, sea, and a street. They're all located in their own folders, and you guys will see more of it when I am actually coding. So let's get into coding. So let's start by importing TensorFlow as TF, and then from TensorFlow we're going to import Keras. After Keras we'll import layers from Keras. And then we want to import TensorFlow hub as hub, because we don't want to write down hub the entire time. So we'll just save ourselves a bit of keystrokes there. So before we get started, we actually have to also install TensorFlow. So we open our Anaconda prompt, and we're going to activate our TensorFlow environment, which is TF in my case. It's named TF. Then going to go pip install TensorFlow _hub. And then it's already satisfied for me, but it should download. It shouldn't take too long, guys. After that's good, we can start to write our code, set our base directory. You can add an int here so that we don't get any formatting warnings from PyCharm. But anyway, yeah, so we're gonna have to set up base directory, and if I just go and show you guys, so our directories is under the data, and this is under this. I'm gonna have to go back 3 folders to get to this folder, and then gonna have to go into natural scenes and then get each of these. The train has like subfolders, so you'll see later with the data generator. I'll explain it. Not the data generator, but getting the data set from the directory. The the files will have to be in this specific like directory structure, so it will have to be in their folders with their corresponding labels. So let's just continue coding. We're gonna go dot dot dot. So this is going back twice, then going back another folder. So go back 3 times. So we're gonna go into data and then natural scenes. PyCharm does that for me. Well, just shows again. After that, we'll make a train dir. So base dir. I'm just gonna add this training path seg train, as you can see from the says seg train over here, and then also we're gonna have to add a forward slash here. Then need a test. We're gonna do tester equal to baster. We also want to make a test directory. This is gonna be seg test. Cool. After that, we're gonna go train dir equals tf dot curious dot util. So now we're gonna actually load the image dataset. So to use this function, you'll have to have the data in this kind of structure. So it has to each of the data each of the images has to be in its specified folder, and the folder's name has to be doesn't have to be the label, but you you will have to you can easily just get the label from this dataset object if you do have them labeled correctly. Also, you're gonna have to make your own dictionary or lookup table for that. Anyway, let's just continue. So, sorry, this isn't train dir, it's train ds. Then, so we have train dir, comma, and then we validation equals, we're gonna do a 0.2 split, so we're gonna have an 80-20 validation, well, train validation split. Then subset, this is gonna be the train subset. And image size is equal to 244 by 244, pretty standard tray or image size for computer vision. Then the seed we're just going to use 42 because that's the answer to the universe, and batch size 32 since that's okay. Where am I? Cool. So yeah, I'm just going to copy paste this and then do the same um, for the test. That's so we just label this test ds. Actually, no, we have to do validation for so let's do val, and then I'm just gonna correctly format this quick. After that, the train this, we have to change this to validation. The seed stays the same, and then everything looks fine. Then we can just copy paste the train once more and make the test ds. Then this would be test dir, and validation. We don't need, just checking, we don't need the validation split. We don't need the subset as well. That's all we need for the train, for the testing in dataset. Right, after that, we're gonna actually load our model from TensorHub. So let me just get to TensorHub real quick. So while we're at Google, we can Google TensorFlow or TensorFlow Hub, and then we have this here. Just click on this. Click on all models, then we'll just get a bunch of, actually we should not do that, should rather go to image. So what we're looking for is a classification model, so we'll pick this. Can scroll down, but we actually want the ResNet. I actually think it might be better if you just search it over here. ResNet 50v2, this is the one that we want, so let's just specifically look for that. Okay, so I think it's this one. Cool. After that, gonna copy that. So we're actually gonna paste this URL up here. Model. Think we'll name this variable model URL. So model URL, and then we'll just copy paste the URL. Cool. That'll just be, we'll use this soon. So we just want to make our model right now quick. So model equal to curious.sequential, then just layers.input. We put our input layer. Then we have shape is equal to 224, 3. The 3 over there is because it's RGB, so it has 3 the dataset has, well, each image has 3 channels, red, green, and blue. After that, we're gonna do layer, no, actually not layers, hub dot curious layer, and then we're gonna plug in our model URL, trainable equals true. So over here, this is where when we're setting basically if you're going to be using a feature extraction or feature or fine tuning. So if this is true, it would be fine tuning it. So it's going to train the entire, like it's going to train the ResNet parameters as well as the the back, not the back end, but the our dense layer that we're building on top of the ResNet, which this is our dense layer activation equals soft max. So yeah, if we had to set this to false, it would just train these this layer over here, which would be about, like, I think ResNet gives 1,000 feature vector of like 1,000. That's dimension is 1,000, and we have a output of 6, so we'll have 6,000 neurons or 6,000 nodes in this dense, and then it would train all those 6,000 weights. Sorry. And I'm just checking if everything's good. Let me just put up a node trainable. So trainable, we can type trainable is equal to true for fine tuning, and then trainable is equal to false for feature extraction. Cool. Let me just, this is apparently correct. Space this out quick. Alright, so looks like we've set up our model. Now we'll do model.compile and loss. So we're going to set our losses to curious.losses dot, my bad, dot sparse categorical cross entropy. Then optimizer will be atom. Cross entropy because it's a multi-class classification problem. Curious.optimizers.atom, comma, then it's metrics is equal to accuracy. Cool. And then we want to fit our model, so let's just fit it to model.fit. Then we're going to train ds, and then validation data is equal to val ds. Then we're going to have epochs equal to 3. Then we'll do model.evaluate, and then we'll evaluate on the test data, test ds, see how we do. Okay, so I think we've just add it into there. Seems like we've got everything in order, so we'll just run this, just set this to current file. You can also just right click and say run, so Control Shift F10, so let's just do that. Right click, run. Cool, so our model trained, and I think the accuracy is not where I expect it to be, so it seems like it did increase a bit, but it seemed to have tapered off with the validation accuracy. Only increased 2%. I think I may know the problem actually. So I did do this mistake in the last video as well, but I'm not sure if you guys caught this, but you actually have to rescale the values. So okay, let me just type this out, 255.0, then we just have to add a comma. So basically the ResNet model doesn't actually rescale the image pixels from 255 down to between 0 and 1. So we need to do that before we put it into ResNet. Some models you'll see, like EfficientNet, do actually do this automatically, so you won't actually need this line. But yeah, for ResNet we will. So You can just retrain that, and then we should be getting a pretty good value. Just like based on, what's it like, 50 lines of code, and we'll get really good results already, which is amazing. But I'll see you guys after this is done training. I'm just gonna run this. Cool. So just based like off of 3 epochs without even like, we actually just used let me just explain the results first. So yeah, after 1 epoch we already got a 88% and 92% validation. It was quite insane, and it seemed to increase a bit. The validation didn't seem to increase that much. We got a test accuracy of 91.6, which is pretty good, and we didn't even train it for that long. We trained it on like 3 epochs. Um, this So one thing to note about feature extraction is that it will probably be a lot less prone to overtraining and overfitting um, when it comes to, I guess, fitting on a data set. And also you'll probably want to use feature extraction on a small data set because it won't overfit it, and it will generalize better to unseen data. If you have a little bit more data, you can use fine tuning, and maybe you can add some data augmentation as well. I think that will yield the best result. Obviously, you can do data augmentation for feature extraction, which I would still highly recommend to get the best kind of model. That feature extraction will probably regularize it already pretty well, but as you can see, it's not actually being regularized. What's Get back to, is this? No, yeah, the run. I don't know why I missed that, but yeah, you can see you're still getting pretty great accuracy. I'll teach you guys how to add data augmentation and maybe even some TensorBoard in the next video. So if you guys have any suggestions for the videos that you'd like me to show you guys, I can just leave it in the comments. I hope you guys enjoyed. Thanks for watching.